There it is. Okay, so this is the iron carbon phase diagram. We have a liquid phase up here and a eutectic reaction where the liquid is transforming to two different solids, gamma iron and Fe3C. That reaction when liquid goes to two solids, that's a eutectic. We also have, and the focus of this phase diagram is a eutectoid phase reaction where gamma phase on cooling transforms to two different solids, alpha and Fe3C. To talk about the give me one sec. Here we go. There we are. We've got delta iron way up here, and cooling it transforms to gamma iron. Cooling it transforms right that temperature to alpha iron. So delta iron up here is BCC in crystal structure. It comes from liquid. So it's the first solid that precipitates from molten iron. And then but we don't deal with it much on engineering materials. The gamma iron is the one that's most important to us. That is called austenite. And austenite is FCC. And note that austenite can hold at up to 2.11 weight percent carbon. This is weight percent carbon is our x-axis. So FCC, iron, gamma iron, or austenite can dissolve up to 2.11 weight percent carbon. And of course that is as a interstitial defect. Carbon, hydrogen, and oxygen can dissolve in iron as an interstitial impurity. And then ferrite, the lower temperature version of iron, is also known as alpha iron, and it is BCC in crystal structure. So those are three of the phases: delta, gamma, and alpha. The other phase is way over on the other end of the phase diagram at 6.67 weight percent carbon. And that phase only has one composition at all temperatures, and it is Fe3C, which we also call cementite. Okay, so those are our phases for this phase diagram. Note that between any two single phase regions is a two-phase region. So here's gamma, up here is liquid. So in between the two, I have gamma and liquid. This line is our cementite, Fe3C. So between liquid and cementite, we have a two-phase region, liquid and Fe3C. Here's my gamma again. Between gamma and Fe3C, I have a region that has both gamma and cementite, or Fe3C. This is gamma phase, this is alpha phase, so in between I have alpha plus gamma. And lastly, I've got alpha, and then over here I've got FE3C, so in between is alpha plus FE3C. And also note that this region, this area in here is ferrite. And once we get down to this temperature, then ferrite just is a constant 0.8% carbon. Okay? Now, as far as steels go, the part of the phase diagram that we are interested in is only this part here. We'll seldom see a steel that has more than 1% carbon. So all of the rest of this phase diagram isn't as important to us, except for the fact that this is where my composition of the cementite is at 6.67% carbon. So I want to look at a number of different temperatures and a number of different compositions, and I want to answer the 3 questions that we can ask of phase diagrams. At any given temperature, composition, what are the phases present? What's the composition of each phase present? And what's the relative amount of each phase present? So this is what I'm going to do. I'm going to want to look at 810. This is what we did in class at 810C, at 730C. This temperature here, this eutectoid temperature, is 727. So I want to look just above it and just below it at 720C. And then I want to look at 400C. Those are my 4 temperatures. My compositions, first we'll look at 0.5 weight% carbon. Then we'll look at the eutectoid composition, 0.77 weight% carbon. Then we'll go back to 0.2, and then finally 1.0 weight% carbon. 4 different compositions, 4 different temperatures. Let's go back and look at 810 for the 0.5. Nope, that was right. That's right, it was 0. Okay. Just wanted to at 730C, I will have 2 phases, alpha and gamma, alpha having formed on the gamma grain boundaries. So I've got alpha and gamma. The compositions of those phases are found by the endpoints of a line that goes at the constant temperature across the 2-phase region. So I'm going to say that that line is at effectively 0.02, not that much different than just right at 727. And I'll say that this line, I can't remember what I used. Hold on, that's not it. Yeah, it is. I'm sorry. Yeah. This, I think I said that this was 0.75. At 730. I believe that's what I said. So, get my black pen back. I've got alpha at 0.02. weight percent carbon, and I've got gamma at 0.75 weight percent carbon. To determine the relative amounts, I can set up a lever. At one end, I've got alpha at 0.02. The other end, I have gamma at 0.75. And my fulcrum is my overall composition, 0.5. So that the percent alpha is going to be the length on the opposite side of the fulcrum from where the alpha is. So it's this length. 0.75 minus 0.5 divided by the total length, 0.75 minus 0.02. And that will be close to 33%. Let me grab a calculator and find out for sure. %. And so the percent gamma would be 100 minus that, 66% gamma. This is 0.5. All right, so that's what we have at just above the eutectoid temperature, 730. When we go to just below the eutectoid temperature, now we're sitting here at 0.5 weight percent carbon. We're at 720 degrees C. So now we have two phases, alpha on one end, and all the way over here where we have the cementite at 6.67. So we have alpha and cementite. So I had gamma, then I crossed the Solvis line, and I had alpha at the grain boundaries. And now, once I cross the eutectoid, the alpha that I had at the grain boundaries is not going to change. That's pro-eutectoid alpha. But where there isn't gamma any longer, there's going to be this microstructure, which is layers of alpha and cementite. So this is alpha pro-eutectoid. And everything else is the eutectoid phase, which is called perlite. Layers of alpha and cementite. That's my eutectoid structure. Okay, so the composition of the alpha, this end, we'll say that's effectively 0.02, and the other end, 6.67. So alpha has 0.02 weight percent carbon, and cementite, Fe3C, has 6.67 weight percent carbon. And so to use my lever to calculate relative amounts, I have 0.02 alpha, and I have 6.67 FE3C, and I'm still sitting at 0.5. So the percent alpha is 6.67 minus 0.5 divided by 6.67 minus 0.02. So that's 93% alpha. And 7% cementite. Now, just a slide ago, when we were at 730, I had let me think here. 5. So I think we had 1/3, about 34% alpha and 66% gamma. And that 66% gamma became perlite. And the alpha that I formed beforehand remains unchanged. So if I look at this alpha, total of 93, that has to include 34 proeutectoid alpha, and then I've got 7 cementite. So the difference here between 93 and 34 is 59% alpha that's in perlite. So perlite is 66% made up of 59 alpha to 7 cementite. So at this temperature, here are my phases and my relative amounts. If I look at microstructures at this temperature, let's see, 720 for 0.5 weight percent carbon steel. Microstructure wise, I should have 66% perlite and 34% proeutectoid alpha. Okay, that is at 720, just below the eutectoid temperature. So I want to make a note of that. So next we are going to cool to 400 C. We're still at 0.5 weight percent carbon. So now we're right here. In the 2-phase region, I've covered this up, but this region is alpha plus cementite. So I got alpha and cementite. The alpha has 0 weight percent carbon. Cementite always has 6.67. Okay, hold on. That wasn't. So now I've got alpha at 0, cementite at 6.67, and I'm at 0.5. So the percent alpha is 6.67 minus 0. Sorry. 6.67 minus 0.5. Divided by 6.67 minus 0, which is, remember, just a moment ago, this was 6.67 minus 0.5 over 6.67 minus 0.02. Not very different. This will still be around 93% alpha. It won't have changed. And for that reason, we don't really worry much about the phases and relative amounts and compositions at lower temperatures because they don't change from what you would get just after crossing the eutectoid. Okay, so that's for 0.5 weight percent carbon. Check. All right, so we're here at 0.77, 810 with our 0.77 weight percent carbon alloy. So it's all gamma. Gamma has 0.77 weight percent carbon, and it's 100% gamma. When we cool from there to 730, just above the eutectoid temperature, we'll still have all gamma. Right here, it's still all gamma. The gamma still has 0.77 weight percent carbon. It's still 100% gamma. The eutectoid reaction for steel is that if I have gamma with 0.77 weight percent carbon and I cool through 727C, this will transform to alpha with 0.02 weight percent carbon plus cementite with 6.67 weight percent carbon. And we really don't need a parentheses there. All right. Now, so this is at 730. When we cross this line, we're going to undergo this reaction. And so now we're here. We're in the alpha plus FeC region. 720. This is 0.77. So the alpha has a composition of 0.02, and this goes all the way out to 0.77. The FeC is 6.67 weight percent carbon. That will always be true at this temperature. Alpha 0.02 weight percent carbon composition. Cementite 6.67 weight percent carbon. So the relative amounts we get from the lever going from 0.02 to 6.67, and my fulcrum is at 0.77. So I have the percent alpha is going to be 6.67 minus 0.77 over 6.67 minus 0.02. So that's 89% alpha. And that means that I have 11% cementite. And it came from all gamma. So that means that these are the two phases I have, 89% alpha and 11% cementite. But all of that at that temperature came from gamma, and gamma makes perlite. So I have 100% perlite. I had 66% perlite for the last example. Here for the eutectoid steel, I make 100% perlite. All right. Let's move to the composition of 0.2. So this would be like a 1020 steel, 0.28% carbon. And we start at 810. We're right here. We're in the two-phase region. I'm going to say that this point is 0.01. And I'm going to say that this point is 0.45. So I've got alpha and gamma, and the alpha is 0.02 weight percent carbon. Oh, I'm sorry, I called that 0.01, didn't I? We said that that was going to be 0.01. And the gamma, we said that was 0.45. So here's my fulcrum. At one end, I've got alpha at 0.01. Other end, I have gamma at 0.45. And my fulcrum is at 0.2. So the percent alpha is 0.45 minus 0.2 over 0.45 minus 0.01. So that's 57% alpha. Okay, this was 0.45. So I've got 57% alpha, and that means I have 43% gamma. So at this point, I've got quite a lot of alpha, and it's formed at the gamma grain boundaries. So this is alpha that's pro-eutectoid. And that's 43%. Nope, sorry, that's 57%. %50 of what I have is pro-eutectoid alpha, and the remaining is gamma. So now we're going to cool from there in the two-phase region to just above the eutectoid temperature. Right here, 730, see? Again, this is my 0.2 weight percent carbon steel. And before I had already said that this is so close to 0.02 that we're just going to say that's 0.02, that point right there. And we know that the other end right here was 0.75. We already determined that. So phases present, alpha and gamma. Alpha has 0.02 weight percent carbon, and gamma has 0.75 weight percent carbon. So here's alpha, 0.02 on one end of the fulcrum, and gamma at 0.75. And I have a 0.2 weight percent carbon steel, so that's my fulcrum. So the percent alpha is now 0.75 minus 0.2 over 0.75 minus 0.02. That's 75% alpha. So that means I have 25% gamma. And so now it's far more alpha than gamma. %75 alpha, 25% gamma. That's just above the eutectoid temperature. So now we're going to cool to just below the eutectoid temperature right here at 720 degrees C. This is still a 0.2 weight percent carbon steel. Now I've crossed into the alpha plus cementite region, ferrite plus cementite. The ferrite has 0.02 weight percent carbon, and the cementite always has 6.67 weight percent carbon. So here's alpha, 0.02. Here's cementite, 6.67, and I'm way over at 0.2. So the percent alpha here is going to be 6.67 minus 0.2 divided by 6.67 minus 0.02. And that's 97% alpha and 3% cementite. So if we think about what this looked like just above the eutectoid temperature, let's see. I think I had something like that for alpha, and the rest was gamma. All the gamma now transforms into perlite, layers of alpha and Fe3C. And above the eutectoid temperature, I had, what was it? I'll have to recalculate it because I don't recall. Above the eutectoid temperature, My percent alpha was 0.75 minus 0.2 divided by 0.75 minus 0.02. That doesn't seem right. I would back up, but I'll lose what I had when we were here. The percent alpha is 75 minus 0.2 over 75 minus 0.02. That's right. So that's 0.55 divided by 0.73. 75% alpha. So oh, that's right. I had 25%. Let me do this here. We've got 97% alpha and 3% Fe3C. Okay. So above the eutectoid temperature, I had 25% gamma. So now I have 25% perlite. And I have 75% pro-eutectoid alpha. And the perlite consists of 3% cementite plus 22% alpha. That adds up to 25. And the alpha that's pro-eutectoid, 75, plus the alpha that's in the perlites, 22, adds up to 97% alpha, which is what I have. Now we're not going to go ahead and look at 400 because just like I said, when we looked at the other compositions, there's not a big change in relative amounts and compositions at lower temperatures. So we are good with calculating this at 720 and confident that that's about how much we'll have any temperature below that. All right, the last composition is the 1 weight percent carbon. And so this steel has more than the eutectoid composition. So this is a hyper eutectoid steel. The others that had compositions less than 0.77, those are hypoeutectoid steels. All right, so we're looking at this at 1.0 weight percent carbon, something greater than 0.77. We're looking at 810 degrees C. So we're in the single phase region, it's just gamma. The gamma will have the composition that you have overall, 1 weight percent carbon, and then there's 100% gamma. Now when this gamma crosses this solvus, line, the gamma crosses that solvus line, then I'm going to start to precipitate not alpha, but cementite in the gamma. So at 810, I have all gamma. But when I cross this solvus line, I'll start to form cementite, which is, it typically is, it etches dark. It will form at the gamma grain boundaries, at the austenite grain boundaries. So this is pro-eutectoid eutectoid, cementite. And the rest is gamma. And so when we look at 730, which is the next slide, we'll be in that two-phase region. So we're here. We're in the two-phase region, so I've got cementite and gamma. No alpha because we're on the right side here at 730. So I'm in the two-phase region. Here's my composition, about 0.79, composition of gamma. And way over here, cementite has a composition of 6.67. So cementite is 6.67 weight percent carbon, and gamma is 0.79 weight percent carbon. And so I've got 6.67 at one end and 0.79 at the other, gamma and FeC, and I'm at 1.0. That's where the fulcrum is. And so the percent cementite, not alpha, the percent cementite is going to be opposite of the fulcrum, so not the long length, but the shorter length, 1.0 minus 0.79 over the total length, 6.67 minus 0.79. So that's 3.5 or 3.6%. We'll go ahead and call it 4% cementite. And that's pro-eutectoid cementite. So this 96% gamma is available to transform to perlite. The 4% cementite stays just like it is. Okay, so we're across the eutectoid temperature right here, 720 C, 1.0 weight percent carbon. We're in the two-phase region, alpha plus cementite. The alpha, 0.02 weight percent carbon. Cementite always has the same composition. 6.67 weight percent carbon. So the percent of alpha, here's alpha, it's at 0.02. Here's cementite, it's at 6.67, and my steel is at 1.0. So the percent alpha is going to be 6.67 minus 1 over 6.67 minus 0.02. That's 85% alpha. And 15% cementite. So when I was at 730, when I was above the eutectoid temperature, I had 96% alpha and 4% cementite. And that's cementite, pro-eutectoid. It's just at these grain boundaries. This was it. Hold on. This was gamma. So this was at 730 just a bit ago. And now I'm going to 720. And the pro-eutectoid cementite that I had doesn't change. It's still there. But everywhere else where I had gamma, it's now perlite. So I've got 85% alpha and 15% cementite. Or another way of looking at it is I've got 96% perlite and 4% pro-eutectoid cementite. All right. The problem with this hyper-eutectoid steel is that this cementite that I've got here in this bigger area, the pro-eutectoid cementite, is very brittle. And so it's possible that I could form a crack someplace, a knot or a pore or some defect, and it would just travel along the cementite in the ferrite plus the cementite pro-eutectoid. So it's very brittle as a material goes. All right. And that, I think that ends my